to continue, we have another local speaker, Zeus Moreira, who is going to talk about quasi-normal modes of an effective loop quantum black hole.
So, hello everyone. Yeah, I will show some results of this work that I've done in collaboration with Haroldo Lima Jr., Luiz Crispino, and Carlos Herdeiro. And I decided to start this presentation with, well, I would say a very strong statement. So, on the slide you may read black holes are plagued with singularities. And from this, put in this way, one might think that a singularity is a defining feature of a black hole. But it's not really this way, right? So we know according to Penrose's theorem on black hole singularities, that in GR, under a certain number of conditions, black holes will have singularities. But there are ways to circumvent the assumptions of this theorem, and people have managed to report several examples of regular black holes. And there is also an expectation that singularities won't be present in a framework of a full theory of quantum gravity. However, it's challenging to work within most of the frameworks of theories of quantum gravity, so a very efficient way to start to see how quantum effects would modify the singularities on black hole spacetime that we know is by proposing some effective models. So in this work, it was reported this line element, which is basically a Schwarzschild spacetime. So this f of r is the familiar metric function of Schwarzschild, but the GRR component, there is this new term, which is a correction motivated by loop quantum gravity, and now it appears here, this R naught, with a new parameter, which takes values over this range, which is called a holonomy parameter. If you consider the surface R equals R naught, it's always enclosed by the horizon, which is located at the same place as Schwarzschild. So here I'm showing a Penrose diagram that represents the global structure of the spacetime. So if you are an observer here in region 1 that is falling into the horizon represented by this diagonal line R equals RH, so as you enter the region 2, you will experience, you will cross several trapped surfaces until you reach this surface R equals R naught, and afterwards you will cross several anti-trapped surfaces on this region 3 until you emerges out in this region 4. So the spacetime is everywhere regular, and the Schwarzschild singularity is replaced by this minimal time-like surface R equals R naught, which represents the global structure of a black bounce. Okay, so in the work, we calculated the scalar quasi-normal modes of the spacetime. So basically, we have to solve this equation for this potential, and there are also some results in this paper. So if you want to have a look, I'm putting here the reference. So I will show our results. So here in this panel, basically, I'm showing the complex plane, and here we have the real parts of the frequency, and here is the absolute value of the frequency. And the quasi-normal modes frequency basically can depend on 3 things. So it depends on the overtone number, n, which have these colors green for the fundamental mode, so green over here, blue for the first overtone, and red for the second one. It can also depend on the L multiple number. So this column here is L equals 0, L equals 1, L equals 2. And it can also depend on the holonomy parameter. So on top of each these segments, we have the Schwarzschild quasi-normal mode. Then as we increase the holonomy parameter, we go down on each segment. And so overall, the role of the holonomy parameter is to decrease the absolute value of the imaginary part of the quasi-normal modes. But there are two segments that have this funnier behavior. So I separate here for a better look. So if we start at the Schwarzschild quasi-normal mode, we are here on the top of each spiral, and as we increase, we spiral down to the quasi-normal mode of the extremum case, and it's a spiral that is self-intersecting. So the spectrum of the holonomy corrected black hole is degenerate. And this spiral behavior was also reported on several other models. I'm just citing a few here. We used the lever method to compute a bunch of overtones of these black hole. So we compute the first study, and here are some results. So I'm showing you several panels with several choices for the holonomy parameter, and we noticed this wave-like structure over the imaginary axis that the spectrum exhibits. And there is a subtlety here. So you may infer that there are frequencies that are located right at the imaginary axis, so with real particle to 0. And that puzzled me a little when I was doing this calculation for the first time, because the lever method could not converge properly in contrast with the other modes. And we put this in the paper and as a caveat, but afterwards there came out this work that replicate our results, and they discussed this, that the lever method in fact cannot be accurate enough to calculate quasi-normal modes with real imaginary part of the frequency. So this is because the roots that you find using the lever method is not stable as you increase the size of the continued fraction. So the results are not reliable. And so maybe there is another method that can calculate this, or you should rethink if the modes that are across this axis are indeed quasi-normal modes. We also computed the time profile. So we basically have to solve this partial differential equation for the same potential that we had before. And this is what we got. So basically, this is a log plot over time from solutions of that equation. And those panels are better understood if we divided them in three pieces. So this first piece is a prompt response that is highly dependent on the initial conditions that we choose. This middle piece is dominated by the quasi-normal modes. And in the end, we have this, at late times, a power law decay. So as you can see, the power law fall off of the two signals, both from Schwarzschild and from the holonomy corrected black hole, they are essentially the same, and you can only differ those signals by the quasi-normal dominated part. We also use the pruning method as a consistency check to extract the quasi-normal modes from that signal, and the results that we got are in great agreement with those that we had with the previous methods. So just some final remarks. Okay, so basically we computed the scalar quasi-normal modes of a holonomy corrected Schwarzschild black hole. And we computed several overtones with different methods. We also analyzed the time profile. Other fields were already calculated by this guy here. But the gravitational perturbations was not explored by anybody. So there is still some room for calculation. And that's all. Thank you.
For the nice talk. We have time for a couple of questions. I have one. How difficult, this is for Schwarzschild, but now what happens if you change this for something like Kerr-like black hole? How difficult is to do these calculations?
Yeah. I don't think there is a clear model of Kerr yet. I'm not aware. It's tricky because these holonomy corrections were first used in cosmological models and then on spherically symmetric models. And there is, as far as I know, a clear way to holonomy correct a Kerr black hole. You can take this one and use some generating technique to give rotation to the solution, but you are not guaranteed to end up with a solution of the same field equations. So you can do it, but you lose a little bit on motivation.
Thank you. Any more questions? If not, then let's